for many years, we were talking about AC9s and BB9s and profiling systems and these radiometers, but they all cost a lot of money. And a lot of people around the world don't have the resources to be able to get these complicated instruments to use. So there are actually some very nice, inexpensive, but robust approaches that you can use to still do good science. And we like, kind of like the icebreakers, over a beer, describing these methods to different students. And they were really requested that we have like a more formal presentation of it. So that's what motivated this these slides. And I first presented this last time with Manuel Voss, and he's not here, and Wayne has been gracious enough to fill in, but also Wayne is like totally revamped a bunch of slides, and they look great. So anyway, to start off, the problem is sensors are expensive, and if you also want to deploy them in large quantities on scales of interest to coastal populations, you just can't do that. There's limits there. So you've got pressure resistant housings, you've got accuracy requirements, limited market, limited resources for some research groups and communities. So the question is, are there inexpensive methods that we can use and still do good science? So yeah, much of the data of interest is near surface. Near the surface, natural variability is large. Obviously, for ocean color, we're interested in surface optical properties. If we can adapt these techniques to other markets, then it creates a larger market. But there are inexpensive but robust alternatives. You want to talk about the cheap electronics?
Sure, but this is more or less in the manual slide.
Yeah, there's like analog, things that I'll talk about, and there's more of this cheap electronics side that Wayne will talk.
Yeah, so sort of building on what and I'm going to try not to call you a manual. What Mike was saying, to do things at the scales we need, we can now buy these very cheap sensors, cheap microprocessors like Arduinos, Feathers, Raspberry Pis. Those are all available. Optics are really available. LEDs, photodiodes, all these things are really easy, and it, like calling it a Lego-like activity to assemble sensors is actually really, really apt. When you couple that also with 3D printing, that's just super available now. You can build a lot of really interesting things for very reasonable amounts of money, orders of magnitude cheaper than commercial sensors. Now we have communication that's via cell phone, that's very straightforward through these same off-the-shelf platforms. Wi-Fi's ubiquitous. Satellite communications is coming. And really importantly, number three, sharing these ideas, putting them on GitHub and Instructables and publishing them in open journals makes it very accessible. So it's super common, and you'll see when I present my stuff that it's very common to put the paper out in some sort of publication, and then just link to the Zenodo or the GitHub that has all the details and all the bill of materials and schematics and CAD models that you need. But like any sensor, like David was talking about earlier, there's associated uncertainties with these measurements. And even though these sensors are cheap, you still need to characterize them in terms of their uncertainties. So yeah.
So the first method I'd like to talk about is this getting beam attenuation C from horizontal visibility with a black disk. This is actually quite a robust approach. So you have a black disk, and it has to be a matte black disk, so you don't want any specular reflection off it. Mounted on a pole, and then you have a periscope that you put in the water. You could also have a diver in the water, and you move the disk along a horizontal path until you can't see it anymore. And you have a tape measure between periscope and the disk so that you can mark the distance. There's a robust theory to this that I'll go into a little bit later on. But you need very, very simple materials to do this. And you can see it's quite robust. So this is a paper from Zonnefield and Pagall from 2003. And beam attenuation coefficient is very strongly linked to this horizontal visibility range. Note that the attenuation coefficient that we're looking at here has a spectral weighting according to your eye, which is a photopic response. So what they were able to do in this paper, though, is to take that photopic response and then regress it, basically correlate it to 532 nanometers. But this, you can get very, very reasonable standard deviations on this over a large dynamic range. For a lot of applications, this would be sufficient for science objectives. This is another paper by Smith and Davies' colleague from New Zealand, where they looked at turbidity versus suspended sediment, and then black disk visibility versus turbidity, which had the best correlation with an R of 0.92, black disk visibility versus suspended sediment, and then black disk visibility versus turbidity on the far right there with a very good relationship. And in New Zealand, this has actually been implemented operationally by the government as in terms of setting criteria for whether or not it's safe to swim in lakes, which is cool. So if the horizontal visibility is less than 1.6 meters, then that's safe to swim in New Zealand since 1994. And that's an official metric that they use. So it's a very simple thing that anybody can go out and make that measurement. Should be larger than 1.6 horizontal visibility. If it's larger than 1.6, you're in this quadrant up here where there's less than 1% of samples fall in high eco light. So this is actually the one I saved to the disk for everybody to have. So I'll just change it. It's a practical, cheap way that people can assess visibility and assess the health of their water in lakes. This is another version of that with a tube with a black disc. And there's a little black disc in there that you fill it with water, and then there's a magnet on the outside, and you can move the disc back and forth with this magnet on the outside. This is all you need is a clarity tube and magnet. You can make your own clarity tube that's calibrated on the side. Or you can buy it. It's very cheap. Yeah, you fill the tube and then you move the magnet back and forth, and you note the distance. And this tube visibility is not exactly the same as the black disc visibility that we talked about before, but they're very strongly correlated. So you can also use this method. This is also sanctioned by the New Zealand government, and it's safe to swim if you have greater than 1 meter visibility with the black disc in the tube method. So moving on to Secchi disk theory. You guys probably all heard of the Secchi disk. How many have deployed a Secchi disk? So almost everybody. Yeah, good. So Secchi disk theory, Secchi disk comes from Secchi from the late 19th century, Italian scientist. But this is the core theory, which is contrast reduction theory. And this can actually be used to basically determine visibility range for a target in any direction. When you're using the human eye, the parameters are for a photopic response. But you've got the apparent contrast of the target here, CR, that's normalized to the inherent contrast of the target. And then you have this exponential, which describes how that target contrast attenuates as a function of distance. And you have attenuation with a range being R, attenuation coefficient C, K, which is diffuse attenuation coefficient. And then you've got this angle. So are you looking straight down, straight up? What angle are you looking at? It's important to realize, and this, let me go to the next slide. So that's the equation we just looked at. And then at some range, contrast between the target and the background will no longer be discernible. You can't see the Secchi disk anymore. As you guys all know, we call that limiting contrast, CL. And then you can solve for V for your Secchi disk range so that your Secchi disk range is essentially proportional to 1 over C plus K. And this natural log of the limiting contrast, which varies for the different detector, which you can use your eye for this, but you could also use a camera. The various cameras you could use. You could have the camera just below the air sea interface or above the air sea interface. You could have it at some altitude above the air sea interface. So there's a bunch of different ways that the CL can be defined. But what's really important here is that the K is not KD from fundamental theory. And if you look at almost any study that applies this relationship to Secchi disk measurements and tries to look at essentially closure between optical property measurements and Secchi disk depth, it almost always everybody uses KD. And the relationship doesn't quite work. It's actually the K is actually the upwelling light from the background around the Secchi disk. It's very different from a KD, which is important. So the issues in applying this this algorithm, there's typically this natural log of limiting contrast can change with different people, with the different eyes, different ability to discern contrast. In Bucata 2005, they saw a range of between 5 and 10. So it can vary, but if you use a camera system, there are ways to kind of constrain that variability. There's also different Secchi disks that people have used. You can use an all-white Secchi disk. You can use an all-black Secchi disk. You can use a black and white quadrant Secchi disk, like the one in the lower right here. What's important in terms of the theory, the fundamental theory, is that the Secchi disk, whether it's white or black, is matte. So it doesn't have any specular reflection. And you guys might remember that when you use the Secchi disk, but most Secchi disks that you buy are very reflective, especially the white part. And that has, I think, a very, very important impact on the final Secchi disk depth that is ultimately derived. Especially then it starts to get dependent on solar zenith and aspects of the environment, which we don't want. The reflectivity of disk, okay, we just talked about that. Shady side versus sunny side. So typically on the shady side, you can see deeper, but that accounts for a lot of the variability that you see in data sets. Cloudy versus sunny, a wavy surface. So the air sea interface, how much glint you're seeing, if it's wavy. Again, you can go through the air sea interface. There are ways to try to reduce the dependency on some of these parameters. Sun elevation again, and I think it's unclear the mechanism exactly why sun elevation affects the Secchi disk, but I think it has a lot to do with reflectivity of the disk. Scattering albedo of the water itself, your eye adaptation, which really goes into that range of limiting contrasts that's observed, and the altitude above the water, as I mentioned. I'll also note that as Jaime Pitarch in his 2020 paper on the Secchi disk, and Dr. Secchi noted that he, in his original paper, noted that these were all issues that could affect the absolute depth that was determined. I'll also note here, I'll also note that Shuba, a co-author in this paper, but there are very cheap ways to make your own Secchi disk printable devices. Do that. Okay, so here's using a view box. So this essentially gets you below the air sea interface, which can remove some variables, but you'll note here in this plot that, sorry about the label there, but the Secchi disk with the naked eye above water versus in water through a viewer box, and you can use a bucket with a clear bottom. There's a bunch of different ways to do this, or just take a camera in a house and put it below the air sea interface. They're systematically different. So interestingly, starting about 2015, Zhangping Li, I wish he was still here actually to discuss this a little bit, but started coming out with a whole series of papers questioning the historical contrast reduction theory, basically saying it doesn't work. And for the way it was being implemented, it really wasn't working. So he came up with a new concept where instead of 1 over C plus K, we've got 1 over 2.5 KD as his approximation for the proportionality to the Secchi disk depth. So the main points in his papers is that he questions the path radiance being the same over the target versus the background. This has to do with once the target's in the water, you start to get you get blurring of the target. You get some near forward scattering around the target. So you get this blurring effect so that it can affect the background path radiance. It'll be brighter directly adjacent to the white target. But this effectively diminishes to nil when you're actually at the Secchi disk depth. What's interesting is the objectives that, or the objections that he comes up with for classical contrast reduction theory. As I just showed you, horizontal viewing works really, really well. You can approximate C very, very accurately. And that is all based and all validated, where it really serves as validation for contrast reduction theory. So he talks about this exception as this may occur because most of the surrounding light over a target in the background are strong radiances in the horizontal direction. It's demonstrated with field observation. So it's not, I don't think, I'd love to discuss this if he was here, just why it works in the horizontal direction, but not the other directions. So that's a question too. So he also questions the definition of contrast as the radiance coming from the target minus the radiance from the background normalized to the background. That has been the kind of classical contrast definition for really since Dunkley and Preisendorfer came up with the whole theory in the 40s and 50s. So he prefers a Weber contrast, or no, he prefers an absolute radiance difference definition of contrast. So anyway, and then there's issues with the size of the disk relative to the spatial dissolving capability of the human eye. But there are ways through other, like basically approaches that complement contrast reduction theory, as I'll show in a second, where you can take into account the size of the target. And this in particular doesn't obviously explain the reasoning for 1 and 2 for me. So what's really important here is in the red is what he came up with is validated with a large global data set. It's really a really huge data set with Secchi disk depth and KD, and validated this and then applied it to satellites. So Zhangping is really clever about developing models and inversions by, in most cases, he takes really strong and highly vetted empirical data, so data that people collect, and then comes up with a theory. And I think, in my opinion, I wish he was here to discuss it, because he makes sure essentially that matches the global data set really well. So honestly, it's just probably the best algorithm we have right now, because we know it does match the global data set. So this is taking contrast, or classical contrast reduction theory, and now adding what's called a modulation transfer function, which is a way to take an image spatially and transform it into frequency space. And if you do that, you can account for things like the size of the disk. So this has the same terms. So this 1 over C minus cosine angle, theta K, this cosine theta, when you're looking straight down, is -1. So it's 1 over C plus K. So this is really the same as classic contrast reduction theory. We have our limiting contrast here, but then we've also added some other terms where we can take into account the size of the disk. So it takes into account two things: the size of the disk as well as the relative contrast of the disk. And this works really well. We've actually applied this. I've done a bunch of modeling on it. We applied it for the Navy in some studies. And you can see here, there's a camera system. So in this case, we're looking up. And we have contrast reduction panels on the bottom of a boat. And we're basically lowering this through the water column. And then the guy from the Navy was looking at a television screen of what the imagery was showing him. And when we couldn't see the contrast of the panels anymore, we'd note the depth. And we tried this in a bunch of different waters, and it worked really well. So at least that algorithm for this application works well. So any questions on that? I guess the ultimate, it's just currently it's a little controversial. And what I think personally, this algorithm works well for the global data set, but let's go back to the other one. So, but if we use the right K, see what happens on all the global data sets, systematically the wrong K, in my opinion, well, as far as contrast reduction theory says in its formulation, the wrong K has been applied. It's KD, but you need KU of the background radiance. So if we applied the right K, and I would also argue that the C is measured with different transmissometers. Remember when we talked about C, that each transmissometer has a different acceptance angle. So there's a wide variety of different C's you can get from different transmissometers. Also, when you're looking at a disk, there's going to be a lot of forward scattering that you still see in kind of the field of view of the disk. So I think that it's work that still needs to be done, and we actually have a new project to look at this in more detail and to actually go through like all of these potential variables, look at like using matte disks versus reflective disks and doing the shady side and the sunny side and use different shape disks and different size disks and stuff like that. So we're going to hopefully systematically go through all of this and try to understand like correct application of contrast reduction theory better. But currently it's kind of amazing. It's been around for 150 years and it's still kind of an open question about the best way to apply or to interpret the Secchi disk in terms of the IOPs. Which for me is actually very exciting. You know, is there even for something that is that historical and that well used around the planet, still there's a lot of work to be done. Any questions about that? Yeah. It does everything, yeah. And you can include lake data, open ocean data, it shouldn't matter. Yeah. One of the things that I need to look into actually when we get back, like as a kind of a kickoff for this new project, is to try to talk to John Ping and see if we can get that data set actually, because we took a lot of different sources to assimilate that. Yeah. I mean, you'd have to, like for instance, the black disk with horizontal visibility. Well, it's like during the day, it's relative, like all those different data points that Sonnenfeld and Pagel had there, they were collected at all different solar zeniths. It's all different azimuths relative to where the sun is too. So it's relatively unaffected by at least ambient solar from any direction. Now, whether or not that means that you could use like your own strobe light or something at night um, is a good question. I don't know. But you know, the thing is when you go out at night and use your own strobe light, you also have behavior of organisms. You have organisms that are attracted to the strobe light and some that are, you know, repelled by this, you know, run away from the strobe light because they are trying to be surface water at night to feed because they're camouflaged essentially. They're hiding. So so yeah, it's a good question. Maybe we should include that in our study. Any other questions? So there's another very inexpensive method to judge color of the water, the 4L Ulys color scale. If you guys have ever used this, but you have these different, you can see the picture here as well. This is a version that you can buy online, but you have these different like numerically distinct color types that 4L Ulys came up with. And you essentially put your cartridge in there, and then you look through here at the Secchi disk, a white Secchi disk in the water, and you can get the color. And then you can. There have been some studies, like Jaime has a great study. This is an example of it being deployed with the Secchi disk, the white Secchi disk there at the bottom. But he's come up with relatively rigorous ways to tie these 4L water types to actual reflectance spectra, as well as spectra of KD. So you can get some pretty good AOP information from the 4L color scale. And he's also shown that you can derive light profiles for far even with this information. I could pass this around, but it's kind of straightforward. Good board here. It's about a 1. So recap, we can potentially solve for the C with the black disk method. That's relatively rigorous. And if we could use the Secchi disk to get not KD, but some other K and understand what that K is. And we actually think we know what that is, but I can't really say it right now. We really need to do the research to prove it. But hopefully, in the next couple of years, we'll have that. But if it's 1 over C plus K with the Secchi disk and you've got the C, then you should be able to then derive some reasonable K value. And if you have a K, there's different relationships that people have come up with, like this guy Gershon, where you can potentially derive absorption information. So then if you have C and A, then you can derive B, that difference. And then there are also biogeochemical proxies, or these optical parameters can serve as biogeochemical proxies. So I love this concept, honestly, and it's something that it's really a concept. The C certainly isn't a concept that's been proven, but kind of the next step is to do the research and to plug in all these. It'd be a nice paper to try to go through this concept of using inexpensive optical approaches, but also validate it with the rigorous stuff, to put error bars on everything in diverse water types. So that's something that hopefully will be done in the future. Any questions? Yep, and then horizontal sighting range with that black disk and Secchi disk have also been correlated with underwater PAR. So there are relationships out there. We're going to move on to Wayne stuff.
I love that one of the simplest, most utilized thing in ocean optics is still an open research question.
Yeah,
It's great. We have jobs for a long time. All right, so I'm going to talk less about the analog side of things and more about inexpensive digital sensors. And I guess, what I would say most clearly is that there's like a major revolution in maker culture and available electronic and optical components, 3D printing, and all these different technologies and things we can buy that will let us develop inexpensive and robust sensors. Some of the examples I'm going to show today, it's sort of a survey of papers and some places that you can look for resources for developing these sensors. But we're going to cover everything from AOPs to IOPs, turbidity sensors, fluorescent sensors, micro imaging systems. And these are applicable to all sorts of different environments and applications, like moorings or buoys, underway flow-through systems, or underway ship track measurements, as well as citizen science. And just also want to credit Emmanuel Boss for this, because a lot of the second half of this I borrowed from him or adapted from him. So the first one I want to talk about that kind of connects to the KD side of things is this system called KDU Pro. And you can see the source there from Carlos Rodero. And on the right, you can see some of the components that go into it. And this is pretty awesome. It's basically a GoPro case and a small embedded microcontroller called a Feather Huzza. It's got a clock and SD card, little prototype board, and very simple circuitry that goes into this, packaged up with a battery. And then on the right, this little RGB sensor, a light sensor. So he's got directions online for about 100 euros. You can build this 3 wavelength irradiance sensor. And basically inside the GoPro box, you've got that RGB sensor right here. And then you put basically some foam around it and then use Teflon tape as a diffuser. And you stick this in the GoPro box connected to the microcontroller, power it, and now you're logging your radiance data. And at 100 euros, you can build multiple of these. You can deploy several at a time to understand the uncertainty. You can put multiple on a single line and throw that over into the water to measure at depths that you define.
I'll just add too that even if you have one that's uncalibrated, you can drop it through the water column to derive K and a very rigorous KD.
Yeah. And so this is an example of doing that profile where you're basically, this is the orange trace is depth, and then the 2 other traces are the irradiance or photosynthetic photon flux density. So it's basically like par, radiant par. And um, it's comparing the KDU Pro, so the homegrown sensor, to a LiPOR, which is a commercial sensor. And they track incredibly well. So this is something that can be, cross-calibrated against other instruments, can be used, like Mike says, as a profiling instrument. So just really amazing for like €100. And if you want, let's say, 4 of these on a string, now you've got €400 plus the cost of string. Another sort of more AOP side of things measurement is using your cell phone. This is an app that was created by Tom Liu when he was at UMaine, and then after he left UMaine and went to Sequoia Scientific. But basically, he designed an app that uses the gyroscope and sort of tilt sensors in a cell phone, the camera, and a gray card to take the measurements that David was talking about today to determine and to make an estimate of RRS at 3 different wavelengths associated with the RGB channels of the camera. And so in the figure here, you can basically see the different measurements that you're taking. You take a gray card measurement in your particular environment. Then you take a sky measurement and your LT water measurement. And this is showing an example of what some of those, what those photos might look like. And then the genius part of this is that the camera deals with a lot of the baggage of having to figure out what your angle that you're actually taking your images at are, where you are in the world and what time it is, so it can figure out what the position of the sun. Really, really kind of an ingenious little setup. And this is showing you what it looks like in this app. And you can download this for both iPhone or Google. He's done a lot of work to build this app, characterize the cameras in these different sensors. And it's pretty straightforward. It basically forces you to take the image of the sky and the water at the right angles, does quality control on it as well. So it's really, really nifty.
It's a free app.
It might be like a couple of bucks, like that. I think it might be to pay for him to buy extra phones so that he can characterize new phones when they come out. But this is an example of some of the data that you can get from this. On the top are 3 different comparisons between RRS coming from the Hydrocolor app versus a WISP, which is a commercial radiometer. And overall, it's quite good. These aren't even log scales. These are like linear scale. Works pretty well. There are some outliers highlighted. He does go over why he thinks that's the case, but works in general quite well. On the bottom, there's an example of using the red RRS as an estimate of turbidity. That also works pretty well, and he validated that against the commercial turbidity sensor. So the very easy clear application for this in citizen science and monitoring changes in places like lagoons or lakes, coastal environment. And to that end, there's actually been some validation of the reflectances acquired by Hydrocolor against a HyperSATS instrument on a ferry in British Columbia. And it's pretty interesting study looking at the statistics of that intercomparison and how it depends on whether the users are trained or untrained. And to summarize the main findings there, that basically it works, but you do need to be cautious that the level of training of the people that are taking the measurements works. That just kind of pans out in our field in general. Speaking of the HyperSATS radiometer that would be mounted on a boat like a ferry, this is another example of a really interesting sort of open source example of somebody in the community taking an existing system and building a really interesting system around it. So this is the Satlantic HyperSATS radiometer system that's been mounted to a open source designed gearbox, stepper motor, solar tractor system, as well as controller box and GPS and everything else. So that's all freely available information. Download it, build these. You want to mount your radiometers on the front of the boat or dock. So getting away from the RRS and AOP sort of side of things, this is an example of a imaging system using a cell phone camera to do microscopy. And just highlighting this particular research group here at UCLA, the OzPan group, they do an incredible range of different imaging systems for like biomedical, especially. And this is an example where they're actually imaging fluorescent nanoparticles using a cell phone camera. It's really wild. Um, this is sort of showing what the system looks like. It basically attaches onto your phone. It adds a lens. It's got a small laser. This is again, you like the plans are out there. You can build this, and then you can actually do microscopy of fluorescent nanoparticles on your phone. So that's applicable to things like almost basically any organism you could label for different things. So it's totally wild. I think they've got a couple examples or a couple of systems that they've designed now for microplastics. Really interesting. This is just showing an example of some of the viruses that they labeled with a marker, and then taking the telephone image, comparing it with SEM, and it's just cool. I don't know how else to say it. Yeah. The device. Yeah, so you can see here in the upper left, that's like a Nokia cell phone. So it's basically the sort of outline of your phone, but a little bit deeper, and it just snaps on the back. Well, in this case, it's just imaging the fluorescence. So I think the pixel size. Yeah, so this is an example of they've actually done marking on the virus. So they've added a fluorescent marker to the sample. So,
Probably depends on the
yeah,
probe.
it depends on the probe. Yeah, I mean, if there's a
There's-
molecular probe for it, and it's a fluorescent probe that has visible emission, should be able to. So yeah, the website that I put on the front there takes you to just a huge array of different devices that they've designed. I'll show another one later.
With
Oh, this is going to be a little bit more expensive than like the €100 irradiance sensor. Just looking at this, that laser diode is probably $100. There's this little Z stage that's associated there. That's probably $100. But then the rest of it looked, and then there's probably some optics. I don't know what it uses for a microcontroller or for electronics rather. But then the rest looks all 3D printed. So it's probably a few $100s, if I had to guess. I didn't dig that deep into this one.
be cool if they posted that online.
Yeah, I
Like-
think that one is. I think that one is. This is an example of an in situ sensor. So this is a group in, I forget exactly where, but they've developed a turbidity sensor that can be deployed in rivers. Well, at least that's their application. It would be suitable for coastal work as well. But they go through the whole process of how they develop the prototypes. They try different optical geometries, different ways of building the sensors, compare it against standards, compare it against sediments. Really, really well done work. I don't recall the cost of this. I think it sort of depends on whether you have your housings machined or 3D print them. But the electronics and optics very simple and straightforward. This gives you an example of the kind of data that they're getting out of this. Where they are is, I think, wherever the Scherzel sediment is, wherever that. So this is an example of SSC, or suspended sediment concentration, that's been measured and estimated based on their turbidity sensor. And these are just showing 3 different ranges of SSC. On the left, the widest range, very, very linear, very, very nice correlation. And then, as you can see, basically it's excellent until you get to these very small correlations, and even that is quite good. And this is, I believe, at least 2 or 3 of their different optical configurations shown all in the same plot. So moving beyond turbidity, this is an example of a fluorometer. And when I first was reading about this, I thought it was just a standard fluorometer giving us, basic fluorescence. And then as I was reading it, I realized it's actually a fast repetition rate fluorometer for like $100. This is incredible. Uses off-the-shelf electronics. I think it's an Arduino. It has a little bit of circuitry in order to make the LED flash fast enough, but it's $100. This is on the right comparing their open source fluorometer against a commercial fast repetition rate fluorometer. This version takes a cuvette, but in their paper they also have a version that could take like macroalgae or a leaf to be able to do FRRF on larger plants. Just this blew me away. I thought this was so cool. And again, open source on GitHub. This is just 2 other examples of some simple sensors, another fluorometer and another turbidity sensor. First one is actually a fluorometer that Tom Liu, the same guy that does hydrocolor, did as a spin-off from an undergraduate project when he was at UMaine. It's basically a little in situ fluorometer that he's built. It goes inside an otter box. It has a battery, a logger, and it's about $150 in parts. The turbidity sensor on the bottom is a handheld unit, like $50 worth of parts, 3D printed case, pretty cool. So this is kind of going in a little bit different direction. This is an imaging system by that same group, on the OSPAN group. This is a very complex system that's been engineered very, very well. And it's essentially a flow-through holographic flow cytometer. And I don't know exactly what their arrangement is. I want to reach out to them. It's patent pending, and there's no source, but they describe the system incredibly well in the paper. The cost of parts for a single unit is about $2,500, but at scale it could be less than $1,000. And I think it might be something that they're going to gear towards being accessible to the community, even if it's not open source. Having a flow cytometer that's imaging that could be less than, even if it's $10,000, is almost an order of magnitude below what it would cost by a commercial system now. So some of these systems, even if they're commercial, they're transformative just because of those same components that are available. They're really neat. This actually is an example of some of the images that they're getting out of this system. It's a really creative way of doing color with a holographic system. It uses neural networks for real-time reconstruction of the hologram. It's really, really neat. So, just an example of that. Yeah, I mean, 25 micron scale bar on the bottom. Pretty cool. Now, this one is open source. This is really cool, and I can't wait to build one of these when I get back to the lab. This is called the Planktoscope, and it's very comparable to a flow cam, which is a commercial flow through microscope that's, we use one at Harbor Branch. They're used all over the place for identifying phytoplankton. They're probably between $50,000 and $100,000. This is $200 to $500 worth of parts to build something like this. It uses a Raspberry Pi. It uses a camera that's commonly used with the Raspberry Pi with some lenses. Has a peristaltic pump. It communicates through Bluetooth. It will log GPS. It's really, really, really cool. And then on the right is actually an example of how it could be deployed. If you deploy a flow cam, you need a laptop. It takes up a lot of space. This is a small little unit. You can see a cell phone here in the lower right. You get the data on the cell phone. It's being powered from a battery pack you would use to charge your phone. This is a great example of disruptive technology, to be able to take something that would normally be, 5 figures and have it be 3 figures in cost. Really cool. This is an example of some of the images you get from that system. The monochrome images are the flow cam, and the color images are from the plankton scope. And they're not, they're not actually imaging coincident particles, but they found ones that are sort of oriented the same way just for comparison. And I mean, it's excellent. The color images, they're crisp, they're just amazing. Amazing. Yeah, again, $500 and like some time for the soldering iron and finding a shop that can print some or can cut some material. Pretty cool. Yeah, so this group in particular, I think Fabienne and maybe some of these other folks are behind the it's a French open like online image classification.
It's like something like CytoSense. That's not quite it, but yeah.
Yeah.
Get the acronym.
Anybody from France know what I'm talking about? It's a open, like a collaborative
Yeah.
machine learning based classification system. I'm drawing a blank on the name of it.
We're using it in our lab too, because we have a shadow graph imager.
Okay.
And there's a whole, we have like 3 people that are working on AI type, like neural network algorithms.
It is described in the paper. It mentions the particular database. I'm drawing a blank on what it is. I'll gonna look it up right after this. But that's an example where they have this online system, and this is sort of tailored to give images to that system, and it will classify it based on community feedback. And sort of in another direction, not just sensors themselves, but some of the tools that we need to make sensors work when we're doing field work. For example, this is a piece of software called Inland, and it's by Niels, who also did the PySAS solar tracking system for the HyperSAS. And it's a modular software-based data logger. It's all written in Python, not MATLAB or anything like that, or C or commercial. Totally open source. It's code that goes on a Raspberry Pi. All the software modules for different instruments are also in Python. Basically, you take all of these different instruments and you have several serial ports, and it takes them all, it merges them together, and timestamps all the data. It processes the data if the processing is available. It's got a real-time graphical interface. So if you have these instruments all connected together on your underway system, you can see everything all in real time. It's cross-platform since it's Python. Really cool. It's been used for the ACS. It's been used for LIST, eco sensors, fluorometers, hyper-BB, CTP data, GPS data, combined it all together. Really cool.
I'll just add that Wet Labs had a data logger,
Yeah.
DH4, that they discontinued a few years ago. So the only data loggers now really available on the market are in like above $100,000.
And they're like huge. They're multiplexers that are typically designed for oil and gas industry type applications and things like that. So
with multiple camera
so
systems.
yeah.
Yeah. Okay.
Yeah.
Yes. Okay.
But I can touch it. Yes.
Look at this.
Yeah, that's good.
Precious things, that's the but
Okay, yeah. It's everything the DH4 did. Yeah.
Cool.
Yeah.
Cool. Couple other examples of these 2 papers. I'm just going to post sort of what they just links to them here. The one on the top is a buoy system that's designed around lines of compact off-the-shelf hobo loggers. They have they're little loggers for all sorts of different parameters. But that's the kind of thing that can be really useful to build systems for aquaculture, coastal water quality, or lake water quality. And then the one on the bottom, I started reading it, that it's basically a whole host of different homegrown sensors that could go on a buoy system. So there's a lot of information in there, but as far as building your own meteorological sensors as well as those things. All right. So we'll finish up nice and early today. We can filter more water. So, like I said, these are only a few examples, and I think, just like I sort of reiterated, there's so many different aspects to this that are cool and disruptive. All these things are cheap. 3D printing is cheap, and like maker culture is I think transforming a lot of measurements that are very societally relevant. Yeah. You want to? I think the other ones are sort of more geared on the analog side of things, but
Yeah, I'll just say that combining the two methods too, like getting the KD plus getting the C with the black disk, like combining the digital analog methods really gives you a nice suite of measurements. And even the ability to validate, cross-validate some of these different techniques as well. So you can actually really get a nice suite of IOPs. And hopefully in research, you validated or determined error bars for your method as well as you can. But this testing closure between between these different methods of making the measurement, it's really a great way of testing the ultimate underlying accuracy and any inherent biases that are difficult to quantify any method on its own. Yeah. Right. Yeah, for things like water quality, like that New Zealand example, I think is a great example where, if you're in the ballpark, in terms of like, that 1% accuracy for something like a black disc, it was enough for them to make a call whether or not it's safe to swim through other coordinated research that was carried out. That's very, very useful. A lot of applications that expensive sensors. Obviously, for the most robust and accurate, like NASA or ESA, Cal-Val, or satellites, you're going to want to use the best sensors on the market. They should pay for that. But for a lot of other applications, there's a lot of good science that can be done with this.
yeah, great example there, like the New Zealand visibility criteria for E. coli. While that measurement might have very large uncertainty, it's easy to make, and you might not have other equipment that can detect E. coli because it's expensive or complex. So it's better to have a measurement with high and known uncertainty than no measurement at all. And that's also a great example of where something like the planktoscope, if you think about this in terms of half, the planktoscope can fill that void because it's cheap, compact, and can be more available. So it's a happy medium that very, very helpful.
Mm-hmm. It's great teaching.